Mr. Roark here. We're going to review concepts. In this video, we're going to review concepts. Mr. Roark here. In this video, we're going to review concepts from Unit 3. Unit 3 dealt with forces. So we're going to review Newton's laws. We'll look at force diagrams, talk about friction, and look at all those concepts that have to do with forces. One of the main things we covered in Unit 3 was force diagrams. So let's talk about the components of a force diagram. In a force diagram, remember, you draw arrows to show all of the forces. So let's say, we know there's going to be a gravitational force on an object. So we're going to draw an arrow straight down, and we need to label that. So we'll put FG. Let's say we know that this object is in contact with a surface. It's sitting on the ground. We know that there's a contact force, and we call that the normal force. So we write Fn. Only put normal force on your force diagrams if it's actually in contact. I see a lot of people that are just throwing those on every force diagram. And it's true, most force diagrams are going to have normal force because most objects are going to be resting on the ground. But if I drop something through the air, it's not in contact with the ground anymore, so there's no normal force on it. It'd be falling straight down. Also, if I have something suspended by a rope, then there is an upward force, but we wouldn't call that normal force anymore. We'd call that force of tension if we have a rope pulling up on it. So you have to be really careful about whether there actually is a normal force or not. Don't just throw it on your force diagram because you think it should be there. Well, let's say there is a normal force in this case. This is an object that's in contact with the floor. And that's pretty much the only forces that are in the vertical axis. Now let's look at the horizontal axis. Let's say that we're applying some sort of push force. So there's my push force in that direction. And let's say we know that there's going to be some friction here as well. Now these are two other forces that you need to be careful of. People are always putting these on force diagrams before they actually think about the forces that are there. If there's nothing actually pushing on the thing that you're looking at, don't put a push force there. Just because it's moving doesn't mean that there's a force pushing it. So if I slide a calculator across the floor, yes, when I am throwing the calculator, I'm pushing on it. But once I let go of that calculator, there's no push force anymore. It's just sliding along the ground, and there would only be a frictional force. This thing would be slowing down because of that. So just because an object is moving doesn't mean there's necessarily a force. You need to think about what forces are actually active there. Same thing with the frictional force. In some situations, we're going to consider friction to be negligible. So if it says friction is negligible, don't put that on your force diagram. Although that's fairly uncommon, we're almost always, from this point on, going to be looking at cases where there is friction. But think about it. Only put forces there that make sense. We're going to say in this case that there is a push force. Now, what else do I need on my force diagram? I have to have directions. If we're dealing with work and energy, then we always want to make forces that are going to speed the object up, positive, and objects that are going to slow it down, negative. So if I was doing this for an energy diagram or a Sloan table, I would want to make sure that my positive force is the push force and my negative force is the frictional force. But that's only because that we don't deal with negative energies. In any other kind of analysis, then it doesn't actually matter. But it's not a bad idea just to get in the habit, so whether you're doing energy or not, it all works out. We also need directions in our vertical axis. We also need forces in the vertical axis, and these don't really matter because the object is not speeding up or slowing down in the vertical axis. We're going to consider this object to be pushed along. Again, that's not always true. In some cases, it may be falling. It may be shot up in the air. You need to think about the situation. And of course, the other thing is we need to fill in any numbers that we know, any calculations. The gravitational force here, we can calculate if we know the mass of an object. Because remember, the other name for gravitational force is weight. And weight is just calculated as m times g. G again being 9.8 meters per second per second. So if you know the mass of an object, then you know what the gravitational force, or you know what the weight is. So we can actually say that this is just m times g, gravitational force. That's our little shortcut, and it's easy to use. Even if you're not going to use it in the actual calculation, you still need to use the mass to find the gravitational force and put it on your force diagram. Now, in the majority of situations, this object is not going to be accelerating upward. It's not going to be accelerating downward. It's going to be either sitting still in that axis or moving at a constant velocity. And in that case, we would know that the normal force has to be equal to the gravitational force. So we can say m times g for the normal force as well. Those two have to be equal if it's not accelerating upward or downward. That is not going to be true in every case. There could be situations where it's accelerating upward or downward. You need to think about that. Yes, in most cases, those two will be the same, but don't just throw it down because you think it should be. Think about the actual situation. Now, in the horizontal axis, the push force, if there is one, is generally going to be given to you. You might actually have to calculate it based on what the object is doing, how it's behaving, but that's going to be something that you're either given or you'll have to calculate. But the frictional force is another thing that you need to know how to find. The frictional force is equal to the coefficient times the normal force. So in a problem, you'd be given a coefficient of friction. We would say the coefficient of friction between these two surfaces is 0.3. And you need to find the frictional force and put that on your force diagram. Now the normal force, as we said, in most cases is going to be m times g. In most cases we're going to look like that's going to be true. And so we can just actually substitute that in. We can say the frictional force here is the coefficient times m times g. These three things you have to be able to calculate for any force diagram that I give you. The push force you might be given, there might not be a push force, whatever, but each of these are going to be common things that you're going to actually have to be able to find and put on your force diagram. Now, what's the point of a force diagram? We want to use this to find the net force. Net force in the y-axis, net force in the x-axis. Those things are independent, so they have to be found independently. Now in this situation, and in many situations, the net force in the y-axis is going to be 0 because it's not accelerating upward or downward, because these two forces are equal in magnitude and opposite in direction, and when you add them together you get 0. But again, that is only in situations where it's not accelerating upward or downward. If you have something that's thrown in the air or is dropped, if it's moving in the vertical axis and it's speeding up or slowing down, then the net force here is not going to be 0. You need to be careful about that. Don't just throw it down as 0 because you think it should be. Think about the situation and actually decide, is it accelerating upward or downward? The net force in the x-axis is going to depend on our two x-axis forces, the push force and the frictional force. And you just add them together once you have your numbers. That's why it's good to draw out the force diagram. If the frictional force is bigger than the push force, then you're going to get an acceleration in that direction. It's going to be, in this case, a negative acceleration, and the object is going to slow down. If the push force is bigger than the frictional force, then you're going to get acceleration in that direction, and the object is going to speed up. If both of those forces are equal to each other, then it's moving at a constant velocity. Net force would be 0, and you would have no acceleration. But the point here is, let's say we get a net force. I'm just going to make up a number so we can talk about it. Let's say the net force here is 60 newtons, so I'm saying the push force is bigger than the frictional force by 60 newtons. It doesn't matter what those actual forces are. It could be 160 for the push force and 100 for the frictional force. It could be 210 for the push force and negative 150 for the frictional force. It doesn't matter what the actual forces are. All that matters is that the push force is 60 newtons bigger. The net force is 60 newtons in the x-axis. And then, once we have that net force, we can use Newton's second law Net force equals mass times acceleration. We can put that net force in here. We can put in the object's mass and calculate what the acceleration will be. This is the gateway between the force diagrams and using the kinematic equations, like the position equation and the velocity equation. Because once you know what the acceleration is, then you can put that into these equations with the initial velocities and things like that and figure out how far it's going to go, how fast it ends up going at a certain point in time, how long it takes to get from one point to the other, or how long it takes to change speeds. But it's all through Newton's second law, and specifically the acceleration. So that's kind of the linchpin between all of this stuff about force diagrams and all the stuff from the first two units that has to do with the kinematic equations and calculating how an object moves. Unit 3, we actually only have a couple of equations. We got this one and this one. So the first one, F equals m times a. We call this Newton's second law. And oh, how many times I've said, what is Newton's second law? And people go, it's an equation. The way Newton set it up, actually, was he said, I want to know how fast an object is going to accelerate. Well, what is that going to depend on? It depends on how hard I push on it, so the force, and it also depends on the mass. But it's a relationship, it's a ratio. When I look at how hard I push on it, the harder I push on that object, the more force I put on it, the bigger the acceleration is going to be. But if I increase the mass, I increase the inertia. Remember, inertia is just an object's tendency to not want to change its motion. And so the bigger the mass, the less the acceleration is going to be. So this is the way Newton actually formulated it. But we write it as F equals ma, so just for ease of memorization. And one thing we need to remember is this really should be the net force. So you have to take into account all of the forces that are working on an object. If there's a force of push, but there's friction, those forces are going to try to cancel each other out. And whatever's left over, if any, I mean, if they're completely balanced, then there will be no acceleration because the net force will be zero. But if there's a little bit left over, either by the friction or by the push force, then that force can cause an acceleration. And so there's another way to look at it. If there is any acceleration on an object, if it's speeding up, slowing down, or changing direction, remember those are three ways that there can be an acceleration. That means there has to be some sort of net force on the object. And so it can be a way to determine, is there something pushing on that object or not? Is it speeding up or slowing down? Yes, there has to be a net force. If not, then either there are no forces or the forces are balanced. Either way, the net force is zero. Okay, the other equation here is for calculating frictional force. It says if I want to know how much frictional force there is on an object, I need to know what its normal force is. And I need to know what the coefficient of friction is between it and the other surface that is involved. So the bigger the coefficient of friction, the more the two surfaces are going to stick together, the harder it's going to be to move. So the more frictional force there's going to be. But we also get an increase in friction if we increase the normal force. Normal force describes basically how much that object is pushed into the surface, whether it's the floor or the ground, or it could be on a wall as well. But anywhere there's contact and you have a normal force, the magnitude of the normal force here tells us how hard those things are pushed together. You can increase the frictional force on an object just by changing how much those surfaces are pushed together. And so those two things can be used to find that frictional force. And that's going to be important on your force diagrams. Because remember, I'm not going to tell you what the frictional force is. I'm going to give you a coefficient of friction. And you're going to have to multiply that by the normal force. But you're only going to be able to do that if you know what the normal force is. And that's why it's good to draw your force diagrams and make sure you label all of your forces.